A quantum physics demonstration contraption. Preparation of wave polarization. View two linear polarizing filters in line with white light behind. Rotate one filter 360 degrees. Observe what happens. How much light gets through as a function of the rotation angle. Why? How? White light is composed of a range of visible wavelengths, each a different color of the rainbow. Refract a slit of white light through a prism, and the colors are dispersed. Focus the colors using a convex lens to reconstitute white light, as Sir Isaac Newton first demonstrated. You may know that light consists of individual and indivisible packets of energy called photons. Each photon has a specific wavelength or color and a polarization, the orientation of the light wave as it travels through space. A photon can be polarized vertically or horizontally, and every orientation in between. From Wikipedia, Malice's law is a function that specifies the percentage of light that passes through a linear polarizing filter. This depends on the angle, theta, between the incoming photon's polarization and the axis of the polarizer, the filter. The function is the cosine squared of this angle, theta. Let's assume the polarization of each photon is the same coming out as went in. Photons emerging from a vertically oriented filter will have various polarizations, all angles except those exactly horizontal. The photons from a horizontally oriented filter will have all polarizations except vertical. Consider white light that has passed through a vertical filter and a horizontal filter. The amount of light that is transmitted through both filters is the intersection of the polarization of photons common to both the vertical and horizontal outputs. And this amount is much greater than zero. This is not what is observed. So we will say our assumption is incorrect. Photons transmitted through a polarizing filter do not retain their original polarization. Let's assume, as before, that the probabilities of transmission are specified by Malice's law. But instead, the polarization of each photon is changed to match the axis of the polarizing filter. We say that the polarization is prepared. Visualize this waving of the light with a specific polarization as a wave on a string vibrating with a specific orientation. Visualize the polarizing filter as parallel slits in a fence. Rotate the slits to change the polarization of the wave that emerges from the fence. Some of the total amount of waving will be transmitted, except for when the slits are perpendicular to the orientation of the wave. Let's simulate a polarized wave using a wave generator and a long cord. A wave generator moves up and down rapidly with a frequency input from the sine wave signal generator. This causes a standing wave to form. The wave vibrates vertically. It is vertically polarized. Let's simulate a polarizing filter using a rotating slit through which the vibrating cord passes. When the slit is vertical, the vertical wave passes through unhindered. Its polarization is not changed. When the slit is horizontal, the vertical wave is completely suppressed. No wave amplitude gets through. When the slit is at a 45-degree angle, say, part of the wave amplitude is transmitted and the polarization of the wave is changed to 45 degrees. Arrange two linear polarizing filters in line with their axes perpendicular so that no light gets through both. Place a third filter at a 45-degree angle between the light source and the first filter. Place it between the second filter and the camera. No change. No light emerges through the filters. Now place the third filter at a 45-degree angle between the perpendicular filters. And surprise, light gets through from the source to the camera. Why? How? Because the polarization of the photons are changed to match the axis of the 45-degree filter. The vertically polarized light that emerges from the vertical filter encounters the 45-degree filter, and some light gets through by virtue of Malice's law. The now 45-degree polarized photons hit the horizontal filter just 45 degrees away, and light emerges polarized horizontally. As before, we will simulate the polarization of waves with a vibrating cord and rotating slits to act as polarizing filters. The wave generator makes a wave that is polarized vertical. Let the vertical wave pass through a vertical filter unhindered. At the horizontal filter, the vertical wave is totally blocked from getting through. Now, rotate the in-between filter to 45 degrees. The orientation of the wave is changed to 45 degrees. Observe that now some of the wave gets through the horizontal slit, as it is only 45 degrees away from the 45-degree polarized wave. Let's review. This demonstration contraption uses the amplitude of a standing wave to represent the probability that a photon with a specific polarization will be transmitted by a filter. The maximum transmission probability equal to 1 is when the polarization of the photon is equal to the axis of the filter.